Hi, my name is Vitaly, and today I'm going to show you the lab of hydrogen and deuterium 2S-nP spectroscopy. And I start off with a brief presentation, and I begin with something you surely know, the energy levels of hydrogen in terms of its principal quantum number n in the Bohr and Schrödinger model. And then, if you compute it relativistically with the Dirac equation, this expression gets more lengthy, and another constant appears, the fine structure constant. Then there is also the recoil effect, which one can compute relativistically. And then it's still not the full picture. There are all these effects from quantum vacuum, which means the effects from the fact that the electron is surrounded by all these vacuum fluctuations. And so the amazing thing for me is that one can really compute all those contributions really precisely and compare it to the measured values. And actually, apart from this so-called lamp shift, there is also the nuclear size effect, which depends on the proton radius. And the reason for that is that actually the electron has a finite probability to be inside the nucleus, so inside the proton, such that it feels how large the proton is. So the iron mass charge radius enters this nuclear size effect. So basically one can summarize this lengthy expression into the more concise form I have here. And here, remember that on the last slide, for simplicity, we ignored the other quantum numbers. So here they appear again, the angular momentum quantum number and the total angular momentum quantum number. And so the energy levels of hydrogen are basically dependent on four natural constants: the Rydberg constant, the fine structure constant, and the electron to proton or deuterium mass ratio, and this proton and deuterium charge radius. There are other constants entering this relativistic and quantum electrodynamic contribution, but they only need to be known very roughly. So basically there are four parameters. And now that means that by doing hydrogen spectroscopy, we can determine those fundamental constants. And what is even more interesting for me is that one can really test these complicated expressions from quantum electrodynamics, and therefore also test the consistency of our fundamental understanding of nature. And last but not least, also this proton and deuterium charge radius contribution also is interesting for nuclear physics. And it turns out that these two constants, the fine structure constant and the electron to proton mass ratio, one can determine from other experiments more precisely, from Penning trap and atom interferometry experiments. So for us in hydrogen spectroscopy, we're left with two parameters, but that still means we need at least two measurements to determine those. And of course, we need even more measurement to test the theory. And in hydrogen, there is this cornerstone of the 1s-2s transition. The reason why it's a cornerstone is because it has a really natural line width of only 1.3 hertz, so it can be measured really precisely using the Doppler-free two-photon spectroscopy. And this astonishing precision was actually achieved here with this setup, with the 1s-2s spectroscopy setup. And in fact, that is actually one of the oldest experiments here at MPQ. And if you look closely here, there is even some date written on the vacuum chamber. It says something like 1994, 1s-2s and 2s-4s spectroscopy. And now we are using this 1s-2s apparatus to measure the 2s-nP transitions. Now what is our measurement principle? It's really simple. We excite transitions between different energy levels with a laser and measure the fluorescence signal. So by slightly detuning the laser, so by slightly changing the laser frequency, we can scan this resonance line and determine the center frequency of this resonance line. And of course, the key requirements for that is that you first need a precise laser. So we use the so-called ultra-low expansion glass cavities, ULE cavities, and we stabilize our laser accordingly to achieve a narrow line width of less than 1 hertz. And furthermore, it's not enough to have a precise and stable laser, you also need to measure the laser frequency precisely, and this is why we need the frequency comb. Now, what is actually our signal? Here I have a level diagram of the 2S-nP spectroscopy. We first start with the ground state, 1s state, and then we have the 2-photon excitation with 243 nanometers to this metastable 2s state. And then we further excite the atoms to the short-lived 6p state with another laser of 410 nanometers, which then decay mainly to the ground state, emitting this high energetic photon with a wavelength of 94 nanometers. And now this photon then hits the walls of our cylindrical detector. So here in the center we have the interaction region, and then this high energetic photons hits the aluminum detector walls, and through the photoelectric effect an electron is emitted and sucked in by this channeltron, which we have on the top and on the bottom of the detector, and we apply an input voltage of around 300 volts, and then these electrons are multiplied inside the channeltron, and this process is achieved through applying a high voltage of about 2 kilovolts. And here actually I have a channeltron, which you probably can zoom in or film it. So this is a channeltron, so one can see this horn-like shape, and we actually use those kinds of channeltrons, but this is basically the same principle. So here the electron gets multiplied such that at the end we have a pulse which we can measure electronically. Yeah, so one challenge for measuring the 2S-nP transitions is that these are dipole-allowed one-photon transitions, and that means we have to deal with the first-order Doppler shift. So the shift of this resonance line proportional to the velocity of atoms. And now if you actually imagine an atomic beam with a velocity vector and a laser beam with another wave vector k with an angle of alpha with respect to each other, then the Doppler shift is proportional to the velocity times the cosine of the angle between the atomic beam and the laser beam. So the first obvious thing to do is to minimize the velocity of atoms. That's why we have a cryosite, which I'm going to show you in a minute, and to align the angle as good as possible to 90 degrees. But then it turns out that for our cryogenic atomic beam and the required uncertainty, we would have to align this angle to better than a microrad, which is simply not possible because our laser beam is divergent and our atomic beam is divergent. So we need an additional strategy for suppressing this Doppler shift. And I won't go into many details here, but the basic idea is to retroreflect the same beam into itself by using this highly reflective mirror. And now, as opposed to the case where you have only one beam, if you have two counter-propagating beams, which have exactly the same intensity and wavefront everywhere, you will get a Doppler shift which is same in magnitude but opposite in sign for the forward and backward propagating beam. So in total, the Doppler shift cancels. So of course, here the whole situation is exaggerated. In practice, you wouldn't see this double resonance structure. And now you somehow shifted the problem to achieving this condition of having the same intensity and wavefront of both beams. And our strategy to do this is this active fiber-based retroreflector, which you can read about in those two papers I have here in the corner. But this is how the setup at the end looks like. We have single-mode fibers, and we have this full-length collimator to minimize all kinds of aberrations. And we retroreflect the beam into itself by using this HR mirror on the other side. And we can rotate the whole setup precisely. And yeah, here we have the atomic beam and 1s/2s preparation laser beam, which cross the 410 nanometer 2s/6p excitation laser at approximately an angle of 90 degrees, which we control as good as possible. With this, let me turn to the experimental side. So first, let me start with the hydrogen supply. Here we have this red hydrogen bottle, and behind there is a smaller deuterium bottle, and so they are connected to the same path. So if we want to do deuterium spectroscopy, we open this path. If we want to do hydrogen spectroscopy, we open this path and close the deuterium line. And then the hydrogen is transferred through these tubes. And here we have a pressure sensor and a flow meter to the discharge. And the reason for the discharge is, of course, that first in the bottle you have hydrogen and deuterium in the molecular form. So you need to dissociate and split the molecules into atoms. And this is what happens in this microwave discharge. We actually use the same microwave frequency as used for Bluetooth or Wi-Fi or in your microwave oven. So it's 2.45 gigahertz. And we have a power of about 40 watts, so about an order of magnitude less than you have in a microwave oven. And here we have this microwave cavity. And of course, if we apply microwaves, it heats the whole cavity. So we first need to ensure the cooling. And this is why I have here a liquid nitrogen dewar. And now I'm going to fill some liquid nitrogen in this small can over here. All right, so you see liquid nitrogen coming out here and boiling. Right. And now I'm going to put in this tube inside liquid nitrogen. And then I'm opening the flow through this tube here. It goes here through these tubes and goes around the microwave discharge, so that basically gas flowing through these tubes is cooled, and then it cools the microwave discharge. So now I'm going to put it in, and you see it's boiling. And yeah, so now we are basically ready to open the hydrogen flow. It's already opened here. So you see here we have about 1 bar of hydrogen in here, but the valve to the discharge is still closed. So I'm going to open it up now, and you see the flow goes up and also the pressure goes up. Right, and now I'm switching on the microwave supply, which is down here. And yeah, probably you can come closer and so that you can see how I'm pressing on the start button. And here it says about 40 watts of microwaves being generated. Okay, so now we have microwaves. And now I need to ignite this discharge. And for this I'm using this Tesla coil. Okay. And I'm going to switch it on. And now ignite the discharge. Right. So hopefully everything works. Right. Yeah. Great. So now we have hydrogen discharge working. And you see this nice magenta color. And this is basically hydrogen plasma where all kinds of excitation takes place. And here I have a picture of the hydrogen discharge and the corresponding hydrogen discharge spectrum. So you see all these Balmer line series at 656 nanometers, 486 nanometers, Balmer gamma, and also Balmer delta at 410 nanometers, which is the same wavelength as, of course, the 2S-6P transitions we are probing. And actually on the bottom, also the Balmer series displayed as a background. Great, so now we have hydrogen atoms. And yeah, probably since we don't need to operate the discharge for the rest of the video lab tour, I'm going to switch off the microwaves again. And you see if I'm stopping the microwave supply, immediately the discharge light goes off because no more energy is provided to dissociate the molecules. So now I'm clicking on the stop button, and you see the discharge light goes off. And I should probably also close the hydrogen supply. All right, so, and yeah, now you see actually the temperature goes down again because I still have the cooling on. So I'm going to switch off the cooling, and now we can continue with our lab tour. Okay, so then the atoms from the discharge are being guided into the vacuum chamber via Teflon tubes. And the reason why it's Teflon, because Teflon as a material minimizes recombination back to molecules. So here, this is how it looks inside. Here on the left, I have a picture of the setup where the chamber roof is lifted up. And here you see this Teflon tube. This is more clearly seen here on the right. And this is the cryostat, which cools this copper nozzle down here. Okay, so this copper nozzle is attached to the cryostat, and the cryostat is cooled to the liquid helium temperature of about 5 Kelvin. And we can directly measure the temperature at the nozzle with this temperature sensor. You see 2 wires coming out. This is the temperature sensor. And then we have a through hole through this copper block where the atoms escape and form an atomic beam if we place additional apertures. And of course, the 1s2s laser beam has to be guided through. That's why it needs to be a through hole. All right, and here actually I have one of the old nozzles. So this is how it looks like. It's basically a block of copper. Here we would attach the Teflon tube. And here, this was still the asymmetrical design where we have the through hole on the left here. Right, and basically the upper side of the cryostat, this is what you see here on the vacuum chamber. And the cooling principle is really simple. We just provide it with a liquid helium, and the liquid helium gets guided through the cryostat and cools this large piece of copper where on the bottom we have the nozzle attached. And now this helium is applied by the doer on the other side of the experiment and is transferred through this transfer line to the cryostat. And now I'm going to show you where it comes from on the other side. It comes from this large liquid helium doer here. It contains about 200 liters of liquid helium. And here the transfer line is currently in. So we could right off pressurize the doer such that the liquid helium goes through the transfer line and to the cryostat. All right, so then we have cooled the atoms since they thermalize in this copper nozzle and escape through the through hole. And now here I have a picture of the inner life of our vacuum chamber with the chamber roof lifted up. So this is kind of the top view. And now here you see basically on the right corner here the Teflon tube from the discharge. Of course, the cryostat is currently lifted up. So here the Teflon tube would be attached from the cryostat into here. And then we would have cold atoms escaping to both sides here, but we actually only use one side. And then we have some apertures here to constrain the atomic beam. And parallel to the atomic beam, as I mentioned previously, we have the 1s2s laser beam. And here we have actually an enhancement cavity to enhance the 243 nanometer light. And then orthogonal to this laser beam, 1s2s laser beam, and the atomic beam, we have the 2s6p laser beam, 410 nanometers, in this rotatable active fiber-based retroreflector setup, where this 410 nanometer light comes from this fiber on the right corner of the vacuum chamber. And you also see here the channeltron on top with some high voltage cable attached here. Actually here we have the detection electronics for the channeltrons and the high voltage supplies here. And then on the outside of the chamber we also have the magnetic field compensation coils. So we also need to compensate the magnetic field and make sure it's small in the interaction region to suppress the Zeeman effect. And actually inside the vacuum chamber we have additionally a magnetic shield. And we also have a Faraday cage inside the magnetic shield to suppress all kinds of electric fields. So here this is basically the magnetic shield. And here you also see these motors for the adjustment of the active fiber-based retroreflector angle. And these two motors up here control the apertures to constrain the atomic beam. And yeah, so outside these are the Earth's magnetic field compensation coils for each direction. And for the vertical direction we have coils wound up actually around the chamber itself. And yeah, why is actually the chamber so big in size? I mean, vertically. This is because we have on the bottom the cryo pump. And if I switch it on, you see that it begins to cryo pump the whole region. And basically, through this cryo pump, we achieve pressure of about 10 to the minus 8, few times 10 to the minus 8 millibar. Few times 10 to the minus 8 millibar, of course. So now with the turbo pump, which we have on the other side of the experiment, here attached we achieve about 10 to the minus 6 millibar, and then with cryo pumping we go down in pressure. Okay, so with this, let me turn to another important part of our lab. These are the lasers. And all of our lasers are basically built the same way. We start with a laser in the infrared. So for example, for the 2S-nP laser, the master laser is here in the infrared at 820 nanometers. And I'm going to open up the box for you so you can see the inside of the laser. So here we have a laser cavity of about 30 centimeters. It's a rather long cavity. And the reason for that is that actually it was found that through longer cavity one is able to suppress the noise pedestal because the Charlotte-Towns limit is reduced. And now inside this cavity we have this electro-optic modulator, which we use for the feedback to stabilize to the ultra-low expansion glass cavity, which I'm going to show you in a minute. And actually here on the grating we also have a piezo element which provides a slow feedback of the laser stabilization. All right, so now I'm going to close the box again because it's not good to leave it open for a long time because of course all the temperatures drift inside and then yeah, it gets unstable. So now let me open up the other wooden box here for you. So the master laser generates 820 nanometer light, and then this light is being amplified in here by the tapered amplifier, and then some of the light is splitted up to monitor the wavelengths roughly with a wavelength meter, and then some other part is splitted up for the ULE cavity, which I'm going to show you in a minute, and some other part is splitted up for the frequency comb, and actually still another part is splitted up for the neighboring experiment, the 1S-3S spectroscopy experiment, to provide a frequency reference and stabilization for their experiment. So this is also a great experiment which will be the topic of another lab tour video. Right, so we have here various parts of the 820 nanometer light splitted off, but the main part actually passes further to the frequency doubling cavity. By the way, we have about 1 watt of infrared 820 nanometer light. And here you see this bow tie cavity with a nonlinear crystal here. And actually here, this left corner mirror, which is the smallest mirror here of 4 mirrors, this is mounted on a piezo such that we can control the length of the cavity. And so now you see that the cavity is locked, so we have nice blue light coming out, 410 nanometers, so twice the frequency of 820 nanometer light. And actually for locking we use this nice simple Hänsch Cryo locking scheme here. For locking to our ULE cavities, which I'm going to show you in a minute, we use the pound-over-hole technique. But actually, most of the work here is, of course, inspired by the ideas and early work of Professor Hänsch. So, for example, this diode laser has been first developed and worked on from Professor Hänsch, so we have, of course, a lot of ideas from him here. Now let me show you the ultra-low expansion glass cavities. So this is this vertical box here, and the idea is really simple. We have basically 2 mirrors which together form the Fabry-Perot cavity. And now the idea is to put in some light from the 820 nanometer master laser through and keep the distance between the 2 mirrors really stable. And it turns out that actually one can really keep the distance between these 2 mirrors to less than 10 to the minus 16 meters, which is less than 1/10 of a proton radius. And it always fascinates me that it's really technically possible to keep the distance between the 2 mirrors to less than a fraction of a proton size, which is basically 100 times or even million times larger than the atoms itself on the mirrors. But it turns out that on average it's possible to polish the mirrors such that indeed the distance between the 2 mirrors is kept to less than 10 to the minus 16 meters stable. And now if you look at the transmission through this cavity, of course you have the, in the intuitive picture you have these resonance conditions that the length must be equal to some integer number, sometimes the wavelength of the laser half. So basically the length stability converts into the frequency stability. And so if we stabilize the length between the 2 mirrors, we get a frequency stability of about 10 to the minus 15, which means about a hertz or even sub-hertz line width. And this transmission signal is then used as a feedback signal for the electro-optic modulators and the grating piezo I've shown on the laser. All right, so now actually the laser got unlocked, and we have a wave meter, which I've shown you in this large wooden box that some light is split off to the wave meter. And actually up there I'm currently looking at the screen to find the right mode. Okay, so it says 820 nanometers, and I know I have to go to around 0.534 or a bit less than that to match the right mode. What I'm actually currently doing is slightly changing the distance in the master laser, which I've shown you in the smaller wooden box. And I'm changing the length by changing the voltage applied on the grating piezo. And now I've found the right mode, and now I have here the transmission signal, which is here on the screen. So in addition to the photodiode, we have also a camera to monitor and to match the right mode. And yeah, actually I can open up the box for you. Then of course the laser gets unlocked again. But right, so this is how it looks inside. So yeah, basically this is a science on its own to make this subhertz line width lasers. There are many tricks involved. So as you see, we have it on the optical table, additionally on this vibration isolation platform, then it's all under vacuum, thermally isolated, and so forth. Yeah, and here we have this photodiode measuring the transmission. All right, so this is how we get the subhertz line width lasers. Actually, the laser still stays locked, so still have the transmission signal. But see, of course, if I'm kind of uncareful, I can bring it out of lock. But the bandwidth is pretty high, so that it doesn't get unlocked. Yeah. Okay. Cool. And yeah, so then, as I've shown you, we frequency double the laser light, and then it transferred to the other part of the lab, and finally enters the vacuum chamber in here, and is guided through this fiber, which is thermally isolated. And here you see that indeed we have blue light entering in here. Okay. And yeah, so here we have actually two optical setup mixed with each other, because we have 243 nanometer laser and 410 nanometer laser. So some of the optical setup belongs to the 243 nanometer laser system, which is basically the same as the 410 nanometer laser system. So we also start with a laser in the infrared, now at 972 nanometers. And we lock it to the another ultra-low expansion glass cavity, which you see on the other side of the optical table. So this, again, this vertical wooden box. And then here we have a commercial system from Toptica, which frequency doubles the laser light twice. Therefore it says force harmonic generation. And so first we get 486 nanometer light. Okay, so it's nice turquoise color. And then after frequency doubling again, we get UV light. And I can also put a piece of paper in the beam path, and you see that UV light is present in the beam. Right, and then the 243 nanometer laser beam is guided through various optical components, and one of them is very important for us. This is this optical chopper here. Okay, so this optical chopper periodically blocks the laser beam. I'm going to switch it on now. So you see that this chopper is indeed rotating. It's rotating with a frequency of about 160 hertz. It takes some time, such that the chopper gets started. And when it rotates with a frequency of about 160 hertz, we can make a time-resolved detection. So the 1s2s excitation laser beam is blocked 100 times a second, and then each time it gets blocked, we trigger our detection signal accordingly to this chopper, and then we record the signal time resolved. So that means after a certain amount of time, after the 1s2s laser has been blocked, we get fewer and fewer fast atoms. So that means the longer we wait, the more fast atoms escape, so we are left with slower and slower atoms. And by this, we can get access to different velocity groups of atoms. All right, and then the laser is guided here further, the 243 nanometer laser, to enter the vacuum chamber through this Brewster window here. All right, so this is the brief overview of the laser system in here. And yeah, let me just finish by showing you the frequency comb, which we of course also need to precisely measure the frequency of this subhertz line-width laser. Now, yeah, just in a nutshell, basically, the frequency comb is a pulsed laser. So in the time domain, you have pulses separated in time, and in the frequency domain, you have this comb separated by the repetition rate frequency. Okay, and there is this offset frequency on the scale, which you also need to know. And then you can basically transform the laser frequency in the optical to the microwave region, or the RF region, which you can electronically count. So I really like this nice picture here, how this is from this review article, how basically a frequency comb converts the high optical frequency, which there is no way to really directly measure, so 10 to the 15 hertz, it converts it to the microwave or RF frequencies, which you can count with frequency counters, which you can see here actually. And then we have our lasers, for example, the 820 nanometer laser light. And if we have a beat node between the comb and our 820 nanometer laser, we can precisely know the frequency of our master laser, since we can log the carrier envelope offset and the repetition rate. And what we actually also do is to log the comb directly to the 820 nanometer light. Yeah, but yeah, just for simplicity, I've shown you this picture. So we keep the repetition rate and the carrier offset frequency locked, and through the beat node with the frequency comb, we can deduce the precise laser frequency of light. This is actually what happens in this beat detection units in here. So you see one of them says 820 nanometers, that's for 2S-6P transition, and the other 972 nanometers for the 1S-2S excitation laser. And now, of course, this assumes that the repetition rate and the carrier envelope offset is locked or precisely known. And this assumes that you have a stable frequency reference. And therefore, we have a maser, which is GPS reference in the other room, which provides us with a frequency standard. So we get about, well, not about, we get exactly 10 megahertz from the maser of the other room, so this black cable, and then we distribute this 10 megahertz through this frequency distribution amplifier. And here actually on the back of the comb, we have this 10 megahertz cable plugged into the frequency reference. Okay, and actually, in order to measure the 1S-2S transition, this maser or GPS reference maser is not enough. So when the 1S-2S frequency was measured, a cesium fountain clock had to come over here to provide basically an even better frequency standard. But for us, since we're measuring the 2S-6P transitions, which are much broader than the narrow 1S-2S transitions, so here we're talking about a 10 megahertz line width, which measured to about a kilohertz, for us, the hydrogen maser is enough as a frequency reference. All right, so with this, I think I mentioned all I wanted to say for this brief lab view, lab tour. And yeah, if you're interested to join our group, or if you have some questions, feel free to contact us. So with this, thank you for watching this video, and probably see you someday in real here in this lab. Thank you.